Hi everyone, welcome to YourPedia and welcome to our interview series questions and concepts for BARC and NPCIL interview preparation. In this video, I'm going to discuss one concept and question that was asked previously in BARC interview and its extension also from the subject power system. The question is from fault analysis. That question is from fault analysis. You all know that there are different short circuit faults and open circuit faults. In short circuit faults, the famous fault or most frequent fault is line to ground fault. The question is, what happens if a line to ground fault occurs on a unloaded generator whose neutral is not connected to ground? Yes. So this is the question asked. This is the question asked. See, for NPCIL also this kind of questions can be asked, but the depth of questions and extension will be there in BARC. That much extension and depth may not be there in NPCIL. If you learn the concept in this way, I can say that you can answer in any interview. But we are going to concentrate for both BARC and NPCIL. The question is, interview ask a question that is, if an LG fault, what is LG? Line to ground fault. LG fault occurs on one of the phases of an unloaded synchronous generator with no neutral grounding. Yes, no neutral grounding. What happens? See, up to what happens will be the question for NPCIL. But if you answer what happens, then how it is happening, can you explain? That will be the question for BARC, extension from there, right? See, there is a small difference between NPCIL and BARC. In NPCIL, just they will ask what happens, you explain the phenomena, that is done. But how it is happening, what it is happening is up to NPCIL. How it is happening, if they ask, that will be BARC. So first of all, what we have to do is one of the very good concept. First of all, what we have to do is we have to take the circuit diagram of what the demonstration given. The demonstration of the question what is given, it's a circuit diagram I have to take, right? Yes, come back. See, he is saying that there is an unloaded synchronous generator. This is phase A. He is saying that its neutral is not connected to ground. Therefore, neutral is there. It means it's a star connected generator. This is phase A voltage, induced EMF EA, and this is phase B, EB. We are talking about AC voltages. This is phase C, AC. Here a lot of things we are going to learn. This is neutral. This is phase A, transmission line, connected to transmission line. This is phase B, please. And this is phase C. This is A, this is B, this is C. Here, neutral is isolated, means it is not connected to ground. Yes, it is not connected to ground. What is the fault we are discussing about? He is saying that on one of the phase, which fault has been occurred? LG fault has been occurred. Let's take on phase A, LG fault is occurred. Let's take on phase A, LG fault is occurred. Yeah, this is phase A. Here somewhere LG fault. Yes, phase A is connected to ground. This is 0 volts, right? Now, what happens is in the normal case when neutral of the generator is grounded. This is 0 volt. Here there will be one circuit breaker and relay. There will be one circuit breaker and relay. Relay is going to detect the fault current. But here the point is very important point. Is there any closed path for the flow of fault current? No closed path for flow of fault current. You see here there is no. See, suppose if you assume, fault current is flowing from phase A, IF or IA or fault current. It is coming from here. Please let me go with a different color. Yeah, it is started from here. It is coming. It is ground to the generator, but no path. Always current flows in a closed path. There is no closed path for the flow of fault current. then a cross question will be asked to you by the interviewer. If there is no closed path for the flow of fault current will not flow. Fault current will not flow. If fault current is not flowing, it's an advantageous condition. He will confuse you. He will ask you a cross question. It is an advantage. No? If you say that, see, if you answer to him, sir, that as the neutral of the generator is not grounded, no fault current is flowing. If you say like this, then he will say that though fault is occurred, fault current is not flowing. It's an advantage. No fault current, but it is not an advantage. Why, sir? See, till here everyone can understand. There is no closed path for the flow of fault current. Then what is happening? First of all, a fault occurred on phase A. That fault must be recognized, must be detected by the relay and circuit breaker. When relay will recognize the fault, if the fault current is flowing through the relay, but is there any closed path for the flow of fault current? There is no closed path. Then what happens, sir? Then what happens? I will tell you. Then what happens? See, first of all, no fault current is flowing through the relay and it is making closed path. Ideally, no fault current is flowing. But practically, small amount of fault current will flow. Small amount of fault current will flow. So how it will flow, I will tell you. See, there is some capacitance of phase A to the ground. Yes. But phase A capacitance or to the neutral, to the reference point 0 volts. Any reference, any 0 volts can be taken as reference. But see, this is 0 volt, this is 0 volt, therefore these two are in parallel. This is 0 volt, this is also 0 volt. This phase A capacitance is neglected. Why? Because in fact phase A capacitance is short circuited with that faulty element. That faulty element is there, no short circuit wire with due to that. But phase B and phase C capacitance will be there, no? Yeah, phase B is there, its capacitance is there. Yes, CBN I call, and phase C capacitance is also there. Yes, let me put here phase C capacitance, that is CCN. Yes, this capacitance is there. Now, actually there is no closed path for the flow of fault current, but there is another small closed path. I can say closed path is there, but very small amount of current is flowing. Then cross question will be asked. You said that there is no closed path. Now we are again saying that there is a closed path for the flow of small amount of fault current through these capacitances. Now see, this fault current which is coming from the generator, yes, coming. Yes, this is the fault point to here. This is the ground. Ground to ground is connected, and this is the ground. Come on, this is the ground of the first capacitor. From here, yes, this way it is making closed path through the phase B. That is one path. Another closed path is means current will be divided into two parts. Yes, another closed path is this one. See, that is one part. Another part is, yes, current from here, yes, to the ground. Yes, this way through CCN. Why? Because if this is ground, this is also ground. Both grounds are same. Yeah, from here it is finding a closed path. Now, next the cross question is, why you are saying that very small amount of current will flow? Why? Because this fault current which is flowing is a charging current. It's not a conduction current. Why? Because the current that is flowing through a capacitor is not a conventional conduction current. It is charging current or displacement current. It will be very small. The first point is this relay, whatever that is present in phase A, in phase B, in phase C. That relay is unable to recognize that very small amount of current. Why it is not large amount? Why? Because it is not conduction current. Conduction is not happening. Why? Because this fault current is flowing through the capacitances. That current is charging current or displacement current. Right? Fault cannot be detected. If fault is not detected by the relay cannot give trip signal to circuit breaker. Circuit breaker is not in a position to open this faulty section from the healthy section. Right? This is the problem. This is the first problem. If neutral of the generator is not grounded, question can be asked this way also. What are the advantages of neutral grounding? If you do the neutral grounding, there is a closed path for the flow of fault current. That is one of the advantage. If neutral is not grounded, there is no closed path for the flow of fault current. Then the fault cannot be detected. If fault is not detected, that cannot be isolated. Fault will persist. Sir, what is the problem if fault persists? Let's see. In this, if fault persists, suppose if there is load here, if there is a load here, what is the voltage across load? This is 0 volt. Due to this LG fault, this is 0 volt, this is also 0, this is 0. Then how much is the voltage that is appearing across the load? 0. How much power is taken by the load? 0. Means my load is not getting reliable power supply because of this one. Suppose if neutral is grounded, then fault current, instead of through these capacitances, it will flow from this ground to this ground directly this way. Yes, that way. Then that fault current is used. We designed our system, we keep relay in such a way that it is going to recognize any current more than its pickup value as fault current, and it is going to give trip signal to circuit breaker. But that is not happening here. Why? Because the fault current is very less. Why? Because the fault current is charging current or displacement current. Therefore, fault cannot be detected, fault cannot be isolated, then load will never get again power supply until you disconnect that fault. Right? Another important problem that is going to happen here is insulation will damage due to rise of other healthy phases. Let's for this one. So if you tell this point, no, then he will ask why other healthy phases voltage is rising. This problem is called as arcing arms or arcing grounds. What is happening here? What is happening here? I will tell you. Observe. See, this is phase B. This is phase B. I want the voltage of phase B. I want the voltage of phase B. If you want voltage, any voltage, you start at that point, again you end at the same point by making a closed path, you are going to get the voltage, right? Now observe here, so this is B, this is also B, this is also B, so VB I want, in fact, VB. For that one, I have to make a closed path. This is the ground, this is VB, please, this is VB, yes, I am writing, see, for that I need to write a KVL like this, yeah, I start here, yes, I go like this, yes, yeah, not this way, sorry, just a minute, yeah, I start here, yes, this is ground, yes, where is another ground, yeah, sorry, just a minute, yeah, come here, I want phase voltage VB, I want phase voltage VB, for that we have to write a KVL, see, voltage is measured between 2 points, that you have to remember. Voltage is measured between 2 points. Now, see, I'm making a closed path like this. You see, I can't come this way. This way is not possible for me to make a closed path. This way is not possible. See, I'm showing here which is not possible. Why? Because there is no closed path here. Why? Because there is no closed path. Then what I have to do? I have to make a closed path through other. So when there is no closed path, I have to make closed path through other way where it is available. Now what I do is, I start here, this is ground, through this ground, yes, this way I can make a closed path. Yes, observe it very carefully, please. Very carefully how to observe, otherwise you will commit mistake in the interview. I want VB, sir. Okay, come to this point. Voltage, for that I am writing a closed path. Yes. This is my closed path, right? Yes. Now I'm writing. Or this way also you can move. This way also, sir, I want VB. Yes, this way also you can move. Yes, you have to make a closed path. That's all. I'm writing here. Observe. I'm writing here. Let me erase these many things. Minus VB, sorry, plus VB. I'm moving to the down. Plus VB. I'm going up to the ground to ground. If this is 0 volt, this is 0 volt, both are connected virtually. Yes. Plus EA, yes, minus EB, yes, minus EB is equal to 0. Then VB, phase B voltage is equal to EB minus EA, that is equal to EBA. I found phase voltage of phase B, but how much I am getting? EBA, which is the line voltage, which is what? Line voltage, right? Unnecessarily, phase voltage is rising up to line voltage because of this charging current or displacement current which is flowing as you did not grounded the neutral. Sir, what happens if I neutral the ground? Let me explain, then we'll go back. See, this is phase A, this is phase B, this is phase C. If the generator of the neutral of the generator is grounded, this is phase A, this is phase B, this is phase C. So here fault is occurred. This is ground, this is A, it may write it as, this is B, and this is C. Now observe here. Observe here. You want phase B voltage. You want phase B voltage. See, any voltage is measured with respect to ground or reference. Yes, VB. Now this is the ground. This is the ground. I write this closed path. I write this closed path. That's all. This closed path. But in the previous one, this facility was not there. You can write now here. So this is plus minus EA. It is. This is plus minus EB. Sorry, minus plus I have to take. Yeah, minus plus it is EB. This is a minus plus it is EC. Write the closed path. So I am writing minus VB. Yes, minus VB. Yeah, here I have a path. See, I am starting here minus VB. I am going like this. I am coming down like this. Minus VB plus EB is equal to 0. Therefore, VB is equal to EB. Here, in this case, if neutral is grounded, means phase voltage is as it is, phase B voltage is equal to phase voltage. It is not rising up to line voltage. But in the previous case, phase voltage rises up to line value of voltage. Right? We write. See, previously here VB I want. Yes, this voltage. I can't go this way because it is open circuit here. Therefore, I moved through other way where there is a closed path. Even if you mean anyway also, you are going to get phase voltage equal to line voltage. If phase voltage is equal to line voltage, what happens? Then the next question they may ask you is, what happens if phase voltage rises up to line voltage? You see, this is the transmission tower. This is the transmission tower, and this is the cross arm. You know, here we are putting insulation, overhead line insulation, and this is your transmission line. This overhead line insulation is designed with respect to per phase voltage. Yes, per phase voltage. Now, if it rises to line voltage, the insulation will damage. If insulation is damaging, means what happens? See, this is designed with respect to per phase voltage. If it rises to line voltage, if this is 0 volt, this transmission line is directly short circuit. It will be a short. See, old insulation damage means nobody is an insulator. It is conducting. Then what happens is, again one more LG fault will occur. So this way phase B, phase C insulation also will fail. Then triple L fault is going to happen, which is more severe than LG fault. And your relays and circuit breakers are not in a position to recognize the fault what that is happening, right? So the point is, if neutral of the generator is not grounded, fault cannot be detected. And fault current is very small, and that is charging current or displacement current. Because of that, healthy phase voltage is going to rise up to line value, due to which again insulation will fail. If insulation fails, that total another two healthy phases insulation is also going to fail. There also fault is going to occur. In turn, completely it is going to become a triple L fault, which is more severe than LG fault. So this is how you have to explain him in the interview, right? So BARC and NPCIL, there is a very small difference. That is, in NPCIL question answer, mostly they won't dig in deep, but for BARC the explanation I given. Now here next question can be like this. That is, what are the different types of neutral groundings? Yes, for NPCIL student, the answers are like this. Sir, there is a solid or effective grounding, means just we are putting one wire, we are connecting from neutral to ground whose resistance is almost 0. That is called as solid grounding or effective grounding. Or the second one is resistance grounding. Third one is reactance grounding. So the answer is done. For BARC, in which case you are going to prefer resistance grounding? What are the advantages of resistance grounding? What are the advantages of reactance grounding? Where resistance grounding is preferred? See, the next question is, where resistance grounding is preferred. Yes, where resistance grounding is preferred and why. Grounding is preferred and why. See, for synchronous generator, the resistance grounding is preferred. Why? Because yes, this here there is an explanation. Observe here. See, we know that acceleration power PA is equal to steam input minus electric power output. Suppose now LG fault has been occurred. If fault occurs, what happens is this electric power output decreases. Therefore, this PA is going to increase. If acceleration power increases, see, if a PA increases, then rotor is going to be more accelerated. If rotor undergoes more acceleration, then stability will decrease. See, if it is undergoing more acceleration, it must have that much deceleration area in equal area criteria. If the rotor is having more acceleration during the starting, then it must have that deceleration area. If that deceleration area is not available, then again the rotor will enter into acceleration. Never the rotor will come to a stable point, and then that generator will be disconnected from the grade Y, because it is going to act like a motor after some angle, after crossing some angle that is 180 degrees, right? So PA is increasing. If PA increases, then stability decreases. Then how to decrease PA? Stability decreases. This is a disadvantage. Power system stability is one of the very important concept for us. Okay. Stability decreases. Then what to do? See, this is PA is equal to PS minus PE without resistance grounding. If you are doing resistance grounding, this is your generator. This is the resistance you connected, Rn neutral. Suppose here fault is occurred. Here fault is occurred. This is the fault current, LG fault. That fault current is having. Yes. Come on here. That fault current is having closed path this way. That fault current is entering here. Now acceleration for PA is equal to PS minus of PE plus I square, IF square into Rn. This fault current is very high. The IF square will be further high than IF square into Rn. This is adding. See, during fault we all know that the electric power output is very less. During fault this electric power output is very less. But this is adding to this. Therefore, when compared to the previous case, in this case, acceleration power decreased. If acceleration power decreases, then rotor acceleration decreases. Then there are fair chances of finding that much deceleration area. According to equal area criteria, deceleration area must be equal to acceleration area. Then it is going to be stable. Right? Then from here again the extension will take place like this. What is the equal area criteria? What are its applications, its limitations? They'll give one simple transmission line. Suppose here the fault is occurred, explain with help of equal area criteria. Mark acceleration area, then deceleration area. If circuit breaker opened its contacts after critical clearing time. So there are questions, critical clearing time, what happens? What is critical clearing time? Right? How you are going to calculate it? And they may not ask you to derive it completely, but the basic method of calculation of that critical clearing time and critical clearing angle, they will ask you. What are the assumptions we are taking while studying this stability? So this way it keep extending. Right? So all the best for all of you. If you have any questions in your BARC or NPCIL interview preparation, yes, you can contact me. This is my contact number 89199999705, and you can contact YourPedia number also. This is my number. You can contact me. I'll help you in your preparation. Right? So this way we will be giving you questions and explanation concepts for electrical engineering subjects. Thank you.